I'm Žikica Lukić. I'm a third-year PhD student from the University of Belgrade under the supervision of Professor Bojana Milošević, and this is a joint work with my academic supervisor. Also, I'm a biostatistician at Parexel. And today, I'm going to introduce a one-dimensional change point test, which is basically a modification of the test of Barinhaus and Kolbe, which can be used in single asset situations in financial markets, and then I'll generalize to the matrix case. Also, just bear this image in mind. I'm going to explain it a little bit later. So this graph. Okay. First of all, we have been motivated by cryptocurrencies and their high volatility. Also, when we developed one-dimensional tests, we wanted to see what happens when you hold a portfolio. For example, when you hold 2, 3, 4 cryptocurrencies at once, since this is not uncommon in econometrics. Also, these tests are just the adaptation of the well-known tests in matrix and one-dimensional cases. So the first object I'm going to explain is the modified Hankel transform introduced by Barinhaus in 2010. So it has this exact form. It has some very nice properties, which are quite similar to the properties of characteristic function. And also it uniquely determines the distribution. There is always in statistics an empirical counterpart, which is going to be used to build a test. And now let's just explain really briefly what is the change point problem. First of all, you have n random variables, which first k comes from a distribution f1, while the rest n minus k come from a different distribution. Also, you don't know where the k is, neither do you know what is the exact form of those underlying distributions. We have proposed the novel test, which is using the idea of Hrushkova and Mentanis, basically adding this part to the already existing two-sample Hankel transform test by Barinhaus and Kolbe, so this part in here. And now let's see some properties of our change point test. First of all, we can compute it in this manner. So we have this part, which is a change point part, and we have this part, which is already computed in the works of Barinhaus and Kolbe. And please bear in mind that this part in here would be important in determining the asymptotic distribution of our novel change point test. First of all, the asymptotic distribution can be expressed in a rather cumbersome manner. So this expression in here is our asymptotic distribution. To be honest, first of all, you need to use that part of Barinhaus and Kolbe, and to compute its underlying asymptotic distribution, to find a covariance operator, and then to compute its eigenvalues. Also, you need to find this expectation in here. Unfortunately, since we don't know what the underlying distribution is, we can't express it further. So we just keep it in this form. If you, for example, said the correct distribution is this and that, this probably could be computed for some specific distributions. We have also conducted a rather small power study. We have estimated the null distribution using 500 permutations, and we have used 2000 repetitions. We have used the uniform distribution, the gamma distribution, with two different sets of parameters. Our main competitors are the tests given in Hrushkova and Mentanis, which are quite similar to our test, but they use characteristic functions to find this expression. If you remember from earlier, this test basically has the same form as our test. Also, it's interesting to see how we have constructed our alternatives. So first, we need to set where the change point is in our simulations. We have used the half of the sample or the quarter. And the alternatives are yn is equal to b, which is a constant, times y1. Y1 comes from uniform or gamma distribution, and plus 1, where we vary the constant b to be either 1 or square root of 2. Also, we have considered sample sizes of 40 and 100 for both cases, and our approach seems to be well calibrated. Also, the powers of the novel test do not significantly depend on the parameter gamma, and change point estimates when we performed the estimation are better in the novel case. Since I don't have unlimited time, if you want to see the exact tables, I'll share it with you in any way possible. But for now on, let's move to the next part. And the next part is totally new. So we have 1 year of Bitcoin data, which hasn't been analyzed in financial literature. So this is the data for the last calendar year, and we have used hourly data. So for each hour, we compute the log returns of the close price, and then we compute the sample variances for each day. So you have 24 hours, and then you compute your sample variance. And then you have 365 sample elements. Also, we have used a binary segmentation algorithm with 500 replications, which is quite basic. But if I have more time, I'll explain it in detail. Also, we needed somehow to verify that those change points really happened. And since we couldn't use the literature, scientific literature, we went to the media and we searched the reputable news sources as, for example, Forbes, as Wall Street Journal, as The Guardian, etc. And we connected our detected change points with actual news on that day or the day after. So those are the news. For example, on 8th of February, if I correctly remember, there was a significant seize of Bitcoin from the Justice Department. Moreover, we have computed the descriptive statistics for our periods, and in here you can see the box plots for each period. Of course, we are going to talk a bit about practical importance in trading later on. And if you remember that graph from the start, it's actually the graph of the Bitcoin close price, where each period is colored differently. So we have segmented our data with respect to this method, and we provided some insights in the behavior of Bitcoin, which is, let's say, totally offline change point detection, but which can be used in validating novel trading systems. Now it's time to go to the matrix case. So quite naturally, we have started investigating it, and we have found that the literature in the matrix case is rather sparse compared to the one-dimensional case. So in 1D, you have many tests, you have many approaches, while in matrix case, for example, for the well-known Wishart distribution, you have only 2 references, which are quite new, so 2020. And also, let's just discuss briefly this object, which is quite similar in matrix case to our Henkel transform in 1D. So this object is proposed by Hadjicosta and Richards in the paper from 2020. And this orthogonal Henkel transform has many properties which are quite attractive. In here, you can see the exact form, while this thing is the Bessel function of two matrix arguments, which can be numerically evaluated in MATLAB, but this is a technical part which I'm going to skip. So if you have any questions, I'm more than happy to answer them. Also, we have provided previously this year a novel two-sample matrix test, which is basically the square integrated difference between two empirical orthogonal Henkel transforms with respect to the Wishart measure. And I'm not going to go into detail how this statistic is computed, but you can find it in this arXiv paper. Also, it has this form when you compute it finally. And now we are going to do basically the same thing. We are going to modify this statistic to detect change points in matrix case, and then we are going to apply it to the financial data. And some interesting things are going to happen. First of all, the problem in this case is quite similar. We still don't know where the change point is. We still don't know the underlying distribution, and our test statistic has a similar form. So we have this maximum, and we have this part, which is basically our previously proposed test statistic. If you try to find the asymptotic distribution, now you're working in a Hilbert space, and it's going to be a little bit challenging compared to the one-dimensional case, but the steps are quite similar, and you are going to obtain a quite similar form of the asymptotic distribution. So I'm not going to state the theorem in here, just so you know it can be computed in a very similar manner. We have conducted also a small power study. In this case, the alternative is constructed as first K observations come from a specific distribution, while the other n minus K come from a different distribution. In here, we have used 500 permutations to simulate the values under null hypothesis, since this test is not distribution free. Also, this is quite computationally challenging, because if you want to compute those test powers, you need large memory to store all of the data. Matrices are quite large, and then you need quite, let's say, powerful processor to compute everything. So this has been done on an ordinary PC, and that's why we have only considered dimensions 2 and 3. Also, if you have more powerful PC, you can probably run it for the higher dimensions. Also, we have concluded that the power generally decreases when you increase the dimension, and then the powers are larger in the symmetric case, which is expected because you have equal sample sizes from both distributions. This test is not sensitive to the value of gamma, as wasn't the 1D case. Also, this test seems to be well calibrated as well as the previous one. And now let's go into some real world applications of the novel matrix change point test. First of all, in front of you, you see some dates which are detected in literature as important Bitcoin dates. What we have done, we have used hourly data for Bitcoin and Ethereum, two most prominent cryptocurrencies. We have computed hourly log returns for both. We have computed covariance matrices for each day. And in here, I'm sorry, we haven't used hourly, we have used minute data in here. So for each minute, we compute log returns, And for each hour, we compute covariance matrices. I'm terribly sorry for the mistake. You can see in here p-values for 2 days prior to the event, up until 1 day prior, the actual day of event and the day before, and the day of event and the day after. In here, you can see the whole period. And when you look into those values, it seems that our test detects the change point quite accurately, except for this case here. But this case here is the announcement that 80% of Bitcoin has been mined. So this thing is closely monitored by traders. So they would approximately know when the 80% of Bitcoin has been mined, and this would influence the price because everyone who is in that business apparently knows the state of the cryptocurrency. Also, this can be seen as an online tool because the periods are very small. If you are interested in day trading, then you are going to have enough time to react when something happens. Also, this confirms that our approach works well on well-documented periods. In here, now we go into hourly data, and we have considered hourly data for the first 6 months of the year. And we have detected multiple change points using binary segmentation algorithm, and we have obtained some change points. Also, we have connected it with the prominent news, which are connected to either Bitcoin or Ethereum. We note that there are many news sources for Bitcoin, while Ethereum isn't that prominent, which is kind of expected. Also, there's the question, what are we going to do with all of those change points in practice? First of all, that single asset analysis is quite useful when you have a bunch of automated trading systems which haven't seen the newest data, and you need to evaluate the performance. Also, you have some automatically detected periods. Some of them are volatile, some of them are not. So imagine you have your investment fund and you just want to see which strategy is most conservative. You use our periods and you evaluate your systems on the newest data. Also, matrix method is quite useful because it uses mini data. It's quite useful as an online detecting tool. So if you are, let's say, a day trader, you are going to get some warning from our test, and you are going to adjust your positions on multiple cryptocurrencies at the same time. For example, you are going to abandon ship because something is drastically changing. And what's most important, this test doesn't require any knowledge whatsoever. It's a plug-in method. You are just going to use your ordinary PC and you are going to get some results. So you don't need any knowledge. And if you want to use, for example, news scraping, then you need a team of programmers which are going to analyze the news, etc. This is way simpler. And the final example for today, we have wanted to see if our dimension reduction approach, which is quite rudimentary, works. So we have selected 28 symbols from DAX, which is a German index for the previous year, which gives us 257 trading days. So the stocks are not traded on weekends and on public holidays, so you have significantly less time. We have computed log returns for each 5-day period, so this is daily data. And we have computed sample covariance matrices for each period. And then we have 52 sample elements corresponding to 52 weeks of the year. Since we have 28 times 28 data, we needed somehow to reduce dimension, and we have done PCA, considered dimensions 2, 3, and 4, also 5, Why? Because in this table here, I don't know if it's visible, but you see that the largest eigenvalue for the dimension 6, for example, is close to 0. And also we have used binary segmentation algorithm, detected change points, and in each case, our algorithm gave us the change point, which is 50. To conclude, we have seen two change point tests, one in 1D, which performs better than its competitors, and the first test, which is a matrix change point test. We have some insight into the uncertainty of covariance estimates, and also there are some extensions. If you remember, there was no weight function added to our square integral statistics. Also, we possibly can consider larger dimensions and a high dimensional case, and also ultra high frequency data. If you remember, our finest data was 1 minute apart. If we were able to obtain data which is sampled every second, then you would have the decision in mere hours, and you could probably use it in real life for some intraday trading. In here, we have just daily trading applications. Also, we would like to see what happens when we use PCA on larger indices. For example, S&P 500, we have just used a very small subset of a very small index to see what happens. Those are the references. And also, if you have any questions, I'm grateful to answer them. Thank you very much.
Thank you a lot, Žikica. Thanks. Super interesting presentation. I have to admit, I know personally Bujana and I listened to it 1 or 2 times. Earlier versions. Thanks. Any questions? This is naturally a super interesting topic also. Random matrices and their applications. I will ask few, hopefully others then as well. I have quite a lot of them. But firstly, you use this for cryptocurrencies, right? So why are random matrices or matrix distributions in particular suitable for modeling cryptocurrencies? Why this? And also you use Wishart distribution and inverse Wishart. There are many matrix distributions, say ensemble things, array functions, mentioned array distributions, and so on, determinantal processes. Could this be extended to other random matrix distributions, and how? And shortly, also 2 short questions for the p-values. How do you do it? I think you mentioned bootstrap, but how to compute for the inference? And also you mentioned PCA. Is this PCA on matrices? This also how to do PCA on matrix data? Maybe I don't know something, but PCA is usually, I think, done on variables conventionally. So what exactly did you do? Thanks. This is a lot.
Okay. Let's answer those questions in order. First of all, we had a hunch basically that you can model the market situation by covariance matrices, so sample covariance matrices, because if something big happens, something would change in the covariance structure. So this is quite a novel idea. And then we tried to develop, first of all, a 2-sample test for matrix inference, and then we tried to apply it and saw that it works quite well. And then we tried using a change point approach, because change points give you more information than, let's say, just a p-value of your ordinary 2-sample test. You can, for example, see where the change actually happens. So this is the first question, if I'm correct.
Yes, surely. Thank you.
Thank you very much. The second question was, can this be extended? Yes, it very much can be extended to any matrix distribution family you'd like. So in here, we have just given some of the alternatives. Also, this list naturally can be extended to any type of matrix distributions. But in here, for example, if that was your question, we have used the Wishart measure to integrate because there were readily made expressions. And in general, when you change this measure, this integral becomes hard to evaluate. So that's why we don't have much references in the literature. So that was the second question.
Thanks.
The third question was how have we computed the p-values? So in 1D case, we used simple permutations, and this was not that computationally expensive, let's say. But in matrix case, if you remember yesterday's presentation from Katerina Halai, she mentioned warp speed algorithm. We have used it for this particular case to obtain p-values in some reasonable time. Also, you can use ordinary bootstrap. It's just too slow on an ordinary PC. So you need, let's say, a day to obtain a p-value, which isn't realistic in applications. So when you have this test as a product and you want to sell it to, let's say, hedge fund executives, you can't simply say, well, this thing is going to take a day because time is money. So this was the third question. And the fourth question was, how did we use this? So basically, you have this 28 times 28 sample matrix, and you can compute its eigenvalues. And you just use the cutoff. You saw the eigenvalues, and you just cut off the second largest, the third largest, fourth, and fifth, and you have those diagonal matrices which have this eigenvalues on the diagonal. This can be used because we use orthogonally invariant transforms, if you remember. We presume that each of those empirical matrices is invertible. This was your fourth question, if I'm correct. I'm sorry if I haven't answered them all.
It's perfectly great. I will give the word to Sophia, but just to briefly mention that the final presentation of the regular sessions on Friday will be by Jana Reker, also on central limit theorem for Wigner random matrices, maybe for you and for others. I just say it will be also interesting to listen as all the others. Sophia, also please, you have time for a question.
Hi, thank you for the interesting presentation. I would like to ask you about the choice of change point detection algorithm. Why do you use binary segmentation? Because it is known in the literature that in case of many change points, it is suboptimal. And there are other algorithms like wild binary segmentation or isolate detect that perform better. So why that choice?
That's actually a great question. Thank you very much. So when we considered how to detect multiple change points, I agree this algorithm is suboptimal, and we have to choose window carefully. In here, we have used window equals to 10. So if you use the window, which is quite large, you are not going to detect many change points, I agree. And if you use the window, which is quite small, you are going to have over detection. Also, we have considered the wild binary segmentation algorithm by, I don't know how to pronounce the surname. It's, you know what I'm referring to, hopefully. But this algorithm seemed as the most simple choice to work with. Also, it would be interesting to generalize this to some data-driven algorithms which may perform better. So this question actually is quite good. Yes, this algorithm can be changed. It can be optimized in a sense, but also when you do this change point, multiple change point detection. You have noted that MB is quite low. It equals 500 because the computational resources are not that big. I hope I answered your question. Thank you very much.
Yes, thank you.
Thank you. I just add we could complicate things and make it patient and then try to optimize the algorithm.
Yes.
Just a joke, but for further work as well.
Yes.
Any further question?